A concrete box. A graphite liner. A concrete box, lined with a graphite liner. Carbon fiber cloth sheet, stitched with carbon fiber thread into the shape of a bowl. The same sheet, impregnated with boron trioxide. Our stack of impregnated carbon fiber sheets. Install the sheets inside the box liner. Empty space. Fill the empty space with boron trioxide. Fill the bowl of the uppermost sheet with boron trioxide. A splash cover. This might be made of ferrosilicon, boron carbide, silicon carbide, borosilicate glass or some other non-reactive material. It rests on top of the graphite liner. Install the splash cover. Fill the empty space between the top of the carbon fiber pile and the bottom of the splash cover with boron trioxide, using the access holes. Fill to the top of the box with boron trioxide. Now, we can begin the nuclear experiment. Part 1 of the experiment. Apply a drop of water on a dry sponge. The water is absorbed by capillary action by the dry sponge, and expands to the greatest volume possible. Part 2 of the experiment. Preheat a graphite crucible for 24 hours to evaporate moisture to prevent a steam explosion. Melt a steel rod into the crucible. Pour the molten steel into the graphite pile, and allow it to cool. Then remove the pile and examine the expansion of the volume of the steel. The steel is absorbed by capillary action into the carbon fiber pile, and expands to the greatest volume possible. The initial volume of the steel. The expanded volume of the steel. This action is somewhat identical to the action of the water on the dry sponge. More precisely, the action of the fluxed carbon fiber pile is exactly identical to the action of fluxed copper desoldering braid in removing molten solder from a circuit board. The melting or sublimation temperature of the graphite is far higher than that of the steel, so there is no danger of damaging the graphite. Carbon fiber is also made of graphite. The melting temperature of the boron trioxide is much lower than that of the steel, and the boiling temperature of the boron trioxide is much higher than that of the steel. So, there is no danger of outgassing of the flux, which will become liquid when exposed to the molten steel. The boron trioxide serves two important functions. 1. It is a fluxing agent, and draws the steel into the carbon fibers, plating the individual fibers with a very thin plate of steel. 2. It plates the graphite so as to insulate it from air or oxygen, preventing any possibility of ignition and combustion of the graphite. Part 3 of the experiment. Build a miniature version of the carbon fiber pile. Preheat a small crucible, probably using a ferrosilicon, boron carbide, or silicon carbide crucible. Take the appropriate radiation precautions, and have the appropriate isotope and radiation detection and measuring equipment operating. Produce corium by melting a small amount of a spent nuclear fuel rod. Melt only a very small quantity of a spent nuclear fuel rod in the crucible, producing only a few drops of corium, and pour the molten radioactive material into the pile. As this video is being composed, TEPCO in Japan is preparing to melt a fuel rod, in order to try to get a better understanding of the core meltdowns in Fukushima, and this experiment could be combined with their experiment. The initial volume of the corium. The expanded volume of the corium. The action of the fluxed carbon fiber pile on the corium is exactly identical to the action of the fluxed carbon fiber pile on the steel. The melting temperature of the boron trioxide is much lower than that of the corium, and the boiling temperature of the boron trioxide is much higher than that of the corium. So, there is no danger of highly radioactive outgassing of the flux, which will become liquid when exposed to the molten corium. The last part of the experiment. After a very thorough and extensive survey of the radiation and isotope data, being certain to check for the creation of any unwanted isotopes, repeat the experiment, but using a larger crucible and a marble-sized amount of corium. If successful, and no dangerous production occurs, continue upsizing with each successive experiment, from a 20th of a fuel rod to an entire fuel rod assembly. The corium will likely release isotopes when heated, but this issue could be resolved by performing the procedure inside of a vacuum chamber, and evacuating any released isotopes into low-pressure storage tanks at the end of the procedure. These waste gases can later be processed into stable solid chemical forms, in most cases, for long-term storage. If successful, theoretically this procedure will kill off most of the fission still occurring within spent fuel rods, eliminating the need to store them in wet pools with circulating water. The fuel rod impregnated carbon piles could likely be stored outdoors behind the nuclear plant on standard pallets, in stacks of 8 piles using 2-foot by 2-foot piles. The radiation and heat production levels should be far less than those of jello cake, or possibly at the same levels as mined uranium ore. There are 2 reasons for this. 1. The spatial volume of the fuel rod is increased 30 to 50 times, which moves the fissile atoms further away from each other by rarefaction, vastly reducing neutron production and interaction. 2. Boron and graphite are 2 of the best neutron poisons, neutron moderators, neutron absorbers. This procedure vastly increases the cross-section and ratio of fissile mass to moderator mass. What little neutron production still occurring because of the considerable rarefaction, would be quickly absorbed by the moderator mass. This procedure of converting spent fuel rods into carbon fiber storage piles should easily eliminate cooled spent fuel wet storage pools, and end all the problems associated with storing, transporting, and dealing with high-level nuclear waste from nuclear power plants. A larger version could be used as a core catcher, making a core meltdown a mere maintenance issue. The procedure also leaves open the possibility of reprocessing the spent fuel. The Vocaloid background music is provided by Iroha. Meltdown, featuring Rin Kagami.